Well, we now have another form of integrating factors. Again, the equation is given in a standard form, m dx plus n dy is equal to 0. And it is known for these equations when del m del y is not equal to del n del x. That means the equation is not exact. So this is an example of an inexact equation. So although del m del y del m del y is not equal to del n del x, it is often found that in some equations del m del y minus del n del x divided by n is a function of x only. X only. So if that is the observation, then the integrating factor for such a situation is del m del y minus del n del x is fx. Then the if is equal to e to the power of integral fx dx. So I repeat, although del m del y minus del n del is not equal to del n del x, the del m del y minus del n del x expression divided by n, that means this expression is a function of x alone. There is again another case in which that expression becomes a function of y alone, but there it will be not n but m. So we will take an example in which this criterion is satisfied, and we will see how the integrating factor of e to the power of integral fx dx does render the equation exact. Let us try to solve this problem in which we have m as 2x square plus y square plus x and n as xy. Now, just to take a check that this particular equation is not exact, what we do is we find del m del y, that we find is this vanishes 2y, and del n del x is just y. So we can say very boldly that del m del y is not equal to del n del x. Hence the equation is not exact and we have to invoke an integrating factor. Let us see what happens when we do del m del y minus del n del x divided by n. We had to find del m del y minus del n del x divided by n, and to check whether it is a function of x only, So in this particular case, del m del y minus del n del x is y. And this divided by n, which is xy. So this divided by n is y divided by xy, is indeed 1 over x, which is a function of x alone. So our integrating factor is e to the power of this fx dx. So the required integrating factor in this particular case is, this was the equation for which the integrating factor is e to the power of fx dx. So the required IF is e to the power of integral 1 by x dx, which is nothing but e to the power of log ex, and that is x to the power of 1. So if we multiply this by x to the power of 1, the equation becomes multiplying by x, we get the original equation will be transformed to an exact equation, and we will get 2x cubed plus y square x plus x square dx plus x square y dy is equal to 0. We rub out this part. We now integrate this, treating this as m, new m, and this as n, which is a new n. So integrate all these terms with respect to x, treating y as constant, and integrate this with respect to y, treating the x constant. So upon integration of this with respect to x and integrating this with respect to y, we get c. When we integrate this with respect to x, we will get 2x4 by 4, so x4 by 2 plus y square x square by 2 plus x cubed by 3, and here we will get x square y square by 2 is equal to c. But this term here in the second integration has already appeared as x square y square by 2. So since we have to ignore any terms in the second integration which have already appeared in the first, we have to ignore this term, and the solution will be these three terms added is equal to c. So that is the solution. C is, needless to say, an arbitrary constant of integration, and the solution has only one arbitrary constant of integration because it is a linear equation. The m dx plus n dy is equal to 0 can be cast in the form as dy dx is equal to minus m by n. That one can verify.